Let's get specific about what we mean by adhere to regularization. Let's get more specific about what we mean by adhere for overfitting. In one form or another, we're going to be looking at this value of the testing cost. We can understand that as the training cost, but with an overfit penalty when we have a case where the training cost and the test cost diverge significantly. Regularization is the first strategy that we're going to look at to understand how to deal with this problem when these two costs diverge from each other. Regularization directly estimates this penalty about how much we should penalize a model or parameterization when there is overfitting. We need to estimate how much to penalize, and that's exactly what regularization does. Try to penalize models that overfit quite drastically with a larger penalty. In validation, which we'll look at a little bit later, we don't do this, but we try to directly estimate how much testing error we're going to get. This isn't usually possible because we're not allowed to look at the testing set, but we can simulate the testing set using validation. We'll see how that's done later on. So what exactly is regularization? It's a cure for our tendency to fit the noise in a signal. And what we want to do is penalize such models such that we can improve our testing cost. Well, how does it work? It works by constraining the model so we can't fit the noise, but there is a significant side effect. When we take this dose of medicine, it's sort of like radiotherapy. We damage our own capacity to fit some part of the signal as well. Let's go back to the familiar example of fitting a sine wave with a line, that is, something in H1. Without regularization, when we took different data samples of just 2 points, we got a very big mess of different types of lines that could be drawn. With regularization as a preview, you can see what happens. We don't get so much variations in lines because we've constrained what magnitude our weights can take. This helps bind the variance to a smaller value and helps constrain the problems when we go on our test data. Going back to our more schematic representation where we took all of those gray lines and for each value of x plotted the standard deviation from the mean hypothesis, we get these gray bars here. By using regularization, we try to constrain the variance, as you can see from this graph. Our red lines have gotten much more narrow in scope. In other words, our variance has gone down. But by doing so, our bias has gone up a little bit, because our model representation is now a little bit less expressive. But the big win is that our variance has stepped down a whole lot, and this is very good for us. You can see now that finally H1 does better than our H0 from the previous lecture. Yay! So what do we exactly mean by constraining the model? Let's take a look at H2 versus H10. Remember, H10 is a 10th order polynomial with weights going up to x to the power of 10. Then what is H2? H2 we can think about also as a 10th order polynomial. It's just that we set all the weights from theta 3 to theta 4 to theta 10, all of the ones that have a coefficient for a cube, for a fourth, all the way to x to the 10th, all equaling to 0. So in fact, we can see that H2 is a proper subset of H10. So in fact, when we say we are using a model in a quadratic form, it's also a 10th order polynomial, just with certain weights set to 0. Thus, we can think about these more restricted lower order polynomials as sort of a hard type of constraint, where we set some weights to 0. But we don't need to be so strict, right? We can find a better way to optimize the setting of the weights for higher order polynomials, just in a way to discourage setting large weights on higher order terms. We're going to do this by the notion of a soft order constraint. A soft order constraint doesn't explicitly set weights to 0. In fact, what we do is something like this. We just constrain everything to fit a particular budget C. We just insist that the weights, or the squares of the weights, have to be below this budget. So we can think about a small amount of C admitting only things like H2, and as we rise up, we increase the budget of C, we can get to more expressive hypotheses like H10. In the limit, when C goes to infinity, we allow ourselves any amounts of weights for everything, and so any hypothesis in H10 is allowable. Of course, we don't have to start at H10. We could go up to H whatever we'd like for 100 or 1,000 if we think that those types of polynomial terms well embody the target function, and like we've said before, we have sufficient data resources to estimate all of those theta coefficients well. You might be wondering why we've decided to pick the square. This is just because it's mathematically convenient for us. So now we've come to an idea between a soft order constraint model that can encompass things between H10 and H2, or any amount that's a large amount, and a small amount. We're going to do this by setting our value C, which is going to allow us to vary between the top and the bottom in a nice flexible manner by dealing with a particular constant budget that we can set. We're going to do it in such a way that the square of all of the weights have to sum up to our constant budget or less. Let's examine this from the viewpoint of linear regression. In our unconstrained, unregularized model, we were minimizing the training cost. This is an average over the individual costs of how bad the predicted value didn't match the actual value with a squared penalty. In vector form, we could write it like this, where we're showing you the vector multiplication of the two terms that are part of the square. We saw from the normal equation lecture that in fact the optimal set of thetas, as indicated by this theta ln, is actually the same as the pseudo-inverse times our column of the target functions. Let's now compare this with what it looks like when we are doing it in the constrained manner where we add regularization. I'm just going to take this form over here and see what's different. Well, these look exactly the same, right? We have the average times the two terms that make up the square. We're going to add in one other term, which is that our weights, which are just the weight vector times itself to get a scalar, must be less than or equal to some constrained constant. So when we apply regularization, we're actually looking at trying to minimize this cost, which is just the training cost with an overfit penalty, where we take the weight squared and constrain it to some budget. The budget is going to be indicated by this variable lambda. We've just divided it over by m to get back what we are using for the training cost. Remember, the training cost is also over 1 over m over some sum of the individual costs of points. Now turning to the graphs, we can see what happens. When we don't apply any medicine at all, we get an overfitting regime. This is the case where we are able to exactly fit the data points that are given to us, but because it's specific to the sample, we might have some coefficients, some of our thetas that take on larger values than need to be. When we just apply a small amount of regularization, you can see it helps a lot. Here, already with this slight preference towards smaller values, we're getting a very, very good match to the target function. When we start to apply too much regularization, you can see it gets to the point where we're starting to underfit because our bias error is going to go up due to the fact that we have taken an overdose of our medicine and have really destroyed our model's capability of fitting a target function. So now a quick question to you, our listener. What happens in the limit as we go from a small amount of lambda to an infinite amount? Take a look at where lambda appears in our function and then convince yourself what should happen. We'll talk about it more in the post-lecture or in class. See you later.